All right, it's a pleasure to introduce Nan Chen, the speaker for our first seminar this semester for numerical analysis. Nan did his PhD at Courant Institute and graduated in 2016. He worked there with the late Andrew Maida, and he stayed on for a couple of years as a postdoc till 2018 when he joined the University of Wisconsin-Madison's Department of Mathematics as an assistant professor, where he is now. His research interests are very broad, which include uncertainty quantification, machine learning, information theory, stochastic dynamics, and related fields, and a lot of applications that he also studies. Today, he will talk about conditional Gaussian nonlinear systems. Nan, thank you so much for contributing to our session, and the floor is yours.
Yeah, thank you, Mohammed. Yeah, thanks very much for inviting me here, and thanks for the nice introduction. And today I want to share some of my recent works about this conditional Gaussian nonlinear system. And this is outline. I will give an introduction, then we'll introduce the system, and I will try to make a connection between the general nonlinear systems with this conditional Gaussian nonlinear system. Then I will try to discuss data assimilation, parameter estimation, and some related topics. So of course, modeling complex systems is a very important topic, especially since last year when the Nobel Prize was about that topic. And actually, these complex nonlinear systems appear in many of the areas, including geophysics, climate science, engineering, neuroscience, and material science. So as mathematicians, we always want to build suitable mathematical models, and these mathematical models will be very important in describing and discovering the underlying physics of these nonlinear systems. I want to mention that modeling nonlinear systems itself is not isolated from others, and actually I want to show this modern applied math diagram from Professor Maida's 2015 ECM talk. And in this diagram, we can see different components that are all connected with each other. So we do need different ways to build qualitative or quantitative models, but we also need rigorous mathematical theorem with novel numerical algorithms. All these things together will help us to understand and try to improve the complex nonlinear systems with a lot of applications. So there are many very important topics in complex systems. So there are some prerequisites for analyzing these systems. Some of those examples are parameter estimation and state estimation or data assimilation. And there are also a few practical tasks, like we try to forecast our future state, especially those extreme events, like extreme weather or climate events. We also want to predict or try to calculate the system's response due to some external or internal perturbations. And when the systems becomes very complicated, we want efficient stochastic or deterministic parameterizations to make our systems simple and easy to deal with. And always keep in mind, there are a lot of mathematical and computational challenges in resolving all these problems. So first, many of those systems will have strongly chaotic or turbulent behavior because of the intrinsic nonlinearity. So we always observe a lot of intermittency, extreme events, and the statistics of these systems will be highly non-Gaussian. Also, many of these systems are very complicated. So if you look at the phase space, then the dimension of the system will be very large, and the systems usually have multi-scale spatial temporal structures. So we have to think about carefully how to design efficient numerical algorithms to overcome these computational difficulties. From a practical point of view, usually we are only able to get partial observations. So you can get the data from the sea surface of the ocean, but not the data in the deep ocean. So we have to design suitable data assimilation algorithms to recover the hidden states and then try to understand nature. And then whenever we think about these issues, always keep in mind there's not a single systems or a single model that is perfect, right? All models are wrong, but some are useful. So we have to think about how to deal with the model error and how to quantify the uncertainty in all these complex systems. And these will be some of the topics I try to emphasize in my talk. Okay, so now let me introduce this conditional Gaussian nonlinear system, this modeling framework. So I will show a lot of examples, and I will motivate you why this kind of system is important. So let me just first give a quick review of this system. So let's say we have a high dimensional state variables. So we split that into two components, an X and a Y. And we try to write this system into such kind of form. So on the right-hand side, and first these four terms, they are basically deterministic functions. And this capital A0, capital A1, lowercase a0, lowercase a1, they are all nonlinear functions of X. And Y here appears in a conditionally linear way. And that means they appear linearly by itself, but they can multiply by any nonlinear function of X. And these last two terms are some stochastic forcing. So this W1 dot and W2 dots, and they are some Gaussian random noise. And these sigma 1, sigma 2, they are coefficients of the noise level. And these coefficients can also be any nonlinear function of X. So these types of system, it is obviously nonlinear, so it can generate non-Gaussian statistics. But there is one very special feature of such kind of system. That is, if assume that we are given one time series of this X, then conditional on this given time series X, and the distribution of this Y will become a Gaussian distribution. So intuitively, you can think if X is given, then all these coefficients, they will be null, right? So in terms of Y, it will be a linear system conditional on this X. And therefore, if it's a linear system with a fixed coefficient for the Gaussian noise, then the statistics will be Gaussian. So that's why we call this a conditional Gaussian or conditional linear system. And this conditional distribution can be completely determined by its conditional mean and the conditional covariance. So as we said, despite this conditional Gaussianity, the joint distribution or the marginal distributions will be highly non-Gaussian because of all these nonlinearities. So actually, later I will show a lot of examples which will belong to such kind of framework. And there's a very nice property here, that is this conditional distribution can actually be solved using closed analytical formula. So we do not need to use any complicated numerical schemes to solve this conditional distribution. But instead, you can see the time evolution of this conditional mean and this conditional covariance can be given explicitly by all those terms related to the model. So we can use this exact and accurate scheme to solve the conditional distribution, which can avoid a lot of numerical issues if we want to solve the distribution using Monte Carlo or other ensemble-based methods. And such kind of closed analytical formula will help us to deal with the systems from a rigorous mathematical point of view, and we can also save a lot of computational cost. So we can study those important topics like uncertainty quantification, data assimilation, and forecast. So then let's see why we consider this conditional Gaussian nonlinear system framework. I will mention two reasons. The first reason is that there are many complex nonlinear systems which fit into this framework. So I listed a few well-known examples. So say for those physics-constrained nonlinear stochastic models, like the Lorentz models, Lorentz 63, Lorentz 96, or 84, and the low-order model of Chinese devolved flows, which is a very famous model in fluids, and a paradigm model for topographic mean flow interactions. This is for like geophysical applications for low-order models. And you can also see there are a lot of examples in the stochastically coupled reaction diffusion equations in neuroscience or ecology. One of those models will be coupled physical Nicomo model, and also SI model will belong to this framework. Then if we look at the atmosphere ocean science problems, you will see a lot of multi-scale models in turbulence, fluids, and geophysical flows that also have such kind of profile, like the Bosniak's equations noise and the stochastically force rotating shallow water equation. So we have a review paper which contain, I guess, maybe 30 to 40 models which belong to this framework. So that says this modeling framework can cover a lot of examples. And I want to show some of those concrete examples. Say the first one is this very simple model, the three-dimensional Lorentz model, which was the first model to describe chaotic behavior, right? So Lorentz has this famous model, which if you plot in the phase space, you will see this very nice butterfly effects. And the system is very chaotic. That means if you start from an initial value that is slightly perturbed, then the forecast value will very soon become very different from the unperturbed forecast value. So this system itself is nonlinear, and only the nonlinear system can give you this chaotic behavior. So you can see this x times z term, x times y term, right? But if we are given a trajectory of this x, then conditional on this trajectory of x, y and z will become conditionally linear, because both of these nonlinearity comes from these quadratic terms, right? So if x is given, then y and z will be conditionally linear. And by the way, I on purpose use blue and pink colors to denote x and y. So throughout my talk, when I discuss this system, if you see blue color, that usually means we can give a trajectory of this variable, and the pink one is a variable that is conditional linear, conditional Gaussian. Another simple example is about these stochastic parameterizations. Say if now I give you a time series of this U, this blue one, you can see there are some of these extreme events, intermittencies, right? So if we just want to use a linear Gaussian model, say if gamma and omega, they are both constant, then you can never capture these extreme events. So what you can do is you try to introduce two separate equations to describe the time evolution of this gamma and omega. So they are kind of stochastically parameterized. Then with these stochastically parameterized systems, the overall system will become nonlinear because gamma times u will be a nonlinear term, omega times u will be a nonlinear term. Then you can get this intermittency behavior. And also regarding those complicated geophysical models, say this Bosniak's equation or Navier-Stokes equation, they are PDEs, but you can always apply a discretization to this kind of system. And say you use a finite Fourier series expansion, then you put some stochastic noise to compensate those truncated part. Then this kind of system will also belong to conditional Gaussian system. So especially if we are given the velocity field, we can recover the temperature, because from the PDE, you can already see that if U is given, then the temperature equation will be a conditional linear system. And for the biology model, this stochastically coupled physical Nicomo model, it is also a conditional Gaussian model. So U here has this cubic nonlinear term, but V itself is a conditional linear. Actually here V itself is even a linear equation. But this physical Nicomo model, if you look at the time series, it can generate a lot of these extreme events. And if you consider spatial temporal patterns, you can see all these very nice intermittent burst events. And lastly, I want to show this very simple example, and I want to point out that conditional Gaussian is not Gaussian. So Gaussian is a very simple distribution, and sometimes people will say it's a very boring PDF in practice. What we really care about is those non-Gaussian behavior. So this is a two-dimensional model, which is a conditional Gaussian model. You can see we have this gamma times U nonlinearity, and we have this feedback term minus U squared. So overall, if you plot the joint distribution, this by no means this is a Gaussian distribution, right? And if you look at the two marginal distributions, both will have this skewed behavior, and especially for this U, it will have a very fat tail here. right? So these marginal distributions are not Gaussian. The joint distribution is not Gaussian, but given a specific value u, like if you put a line here, then this slice, the distribution along this slice, it will be Gaussian. So it's only a conditional Gaussian distribution. It's not a Gaussian distribution. So that's why this kind of system can describe a lot of phenomena in nature, because nature is highly non-Gaussian. But there will be certain component in this complicated nonlinear system, which is Gaussian, that is a conditional distribution. Okay, so so far we discussed a lot of systems and themselves already belong to this framework. But of course, there will be many more systems which do not have this conditional Gaussian profile, right? Otherwise, we are done with all the work. But still, these conditional Gaussian systems can be very useful because they can be used as a fast preconditioner and a cheap surrogate model for those general nonlinear systems. And here I use this figure to illustrate how this works. So if we start with a general nonlinear system, because it's so complicated with a very large phase space, usually it will make it impossible to have some fast algorithms to do data assimilation or forecast or other things. But what we can do is we can start with this system and we make some approximations to find a conditional Gaussian model as a surrogate model for this original system. Then if we only care about some direct output, say if we only care about the forecast scale, we can always use this surrogate model to do the forecast, right? But if we care about some intrinsic features of the original system, say if we want to study some feedbacks, or if we want to estimate the parameters in the original system, then we can still use this conditional Gaussian system as a preconditioner. So we can try to, for example, we can try to use a conditional Gaussian system to find some good initial conditions to do the parameter estimation. Then we only need to use the original system for like 1 or 2 steps of iterations. So it can save a lot of time for us instead of using the original system from scratch. So now you must ask me how we can start from a general nonlinear system and to build a conditional Gaussian system. So I want to briefly mention about one very simple idea here. So I want to start from the general turbulence systems motivated from the fluids and the geophysics, and it has such a profile. So U is our state variable. On the right-hand side, we have this linear damping term, and this phase term D here. So L is negative definite, it's damping or dissipation. D is skew symmetric, representing the rotation or the phase change. And this BUU is a quadratic nonlinearity, and usually it is energy conserved. We will also have some deterministic forcing, and sometimes you have this stochastic forcing, but sometimes you don't. So that's not so important. So what you can do is usually you try to decompose your original state variable into different parts. Say we decompose that to V, W, and Z. And V is the largest scales, W is the medium scale, Z is the small scale. Usually you try to ignore your small scale. You always do some truncation when you do discretization. So you project your U to the large and medium scale variables V and omega, right? And so you can write down like these 2 separate equations, but they are coupled. They have linear terms, and they should have these 3 different nonlinear terms, representing the nonlinear interaction between V itself, the cross nonlinearity between V and W, and the WW itself, right? Just try to rewrite this BUU term. Think U is V and W, but you try to ignore Z. So you should have VV, VW, and WW. So similarly, you also have these 3 parts in your second equation. And this system, of course, it's not a conditional Gaussian system, because if we treat W as this Y, this term is okay, this term is okay, this term is also okay, but this term is not okay, right? We cannot allow these quadratic terms here, because Y, we only allow it to appear in a conditionally linear way. So what we can do is we try to use a closure method, and simplest closure method, you try to replace these purple terms by some closures. And for the closure, we can on purpose try to use a conditional linear function for this W. So we can include arbitrary nonlinear terms for this V, but for W, it's a conditional linear system, right? So then this overall model will become a conditional linear conditional Gaussian system. So of course, here we make some approximations, but try to think V is a smaller scale variable compared with this V. Sorry, W is a small scale variable compared with V. So this nonlinear term in terms of the W times W, usually it will be a fast component, and it will also contain smaller energy compared with other terms. So approximating such kind of term is overall justified in many of the applications. And then you may ask me how to estimate the coefficients of the closure. So if we have the time series of both V and W, then we just apply a linear regression for the coefficients. But if we have only the partial observation, say if we only have the observation of V, then we have to do an expectation maximization algorithm, try to estimate the coefficients and try to estimate the hidden states simultaneously, which I'll briefly mention later in this talk. But anyway, here I just want to say there will always be a systematical way to provide a system which is a conditional Gaussian system as an approximate model for the original nonlinear system. Okay, so now I want to move on to some topics where the conditional Gaussian nonlinear systems can be practically useful. And the first topic is about data assimilation and related the ensemble forecast. First, I just want to provide some very basic background. So what is data assimilation? So data assimilation is a method that tries to find the optimal combination of a numerical model with observations to improve results. And it is a very important and famous method that is widely applied in many of the areas related to turbulence, say climate science or atmosphere ocean science. So why we need data assimilation? Why we don't just use a model or just use observations? Because a model is typically chaotic and has uncertainties. You will have certain stochastic noise in your model, and your model may have some model error. So completely trusting a model will lead to big issues. And on the other hand, you will also have observational noise in your observations. And as I said, we may only have partial observations. So we cannot completely rely on observations either, because that will not provide us a complete information. And that's the motivation. You have to combine these two things together. So usually we start from some initial value at time tm. We try to use our model to do a forecast until time tm plus 1. And because our model has uncertainties, so a forecast is in the statistical sense. So it will give you a distribution instead of a single value. Then you combine your forecast value with your observations. And the observations usually will not be the same as the forecast. So they will have two distributions. Then you combine these two distributions together in certain optimal way, you will get a better state estimation that will be, in principle, closer to your truth. But closer means your like the mean or the mode will be closer, but still you have some uncertainties. And mathematically, this data assimilation is very simple. It's just this Bayesian theorem. So you try to forecast a model first, which will give you a prior distribution. Then you treat your observation as a likelihood, meaning that how possible your forecast value will be located in the distribution from the observation. Then you multiply them together using the Bayesian framework, you can get a posterior distribution. That means the forecast state given the observations, right? With this additional information, it should be, in principle, more accurate than just using the forecast model. However, despite the very simple mathematical formula, in practice, as we know, if we want to solve this distribution in a very high dimensional space, it's almost impossible analytically, unless you have a Gaussian distribution. So usually in practice, we try to use ensemble-based method. But the issue is the ensemble-based method will have some numerical or sampling problems, especially in high-dimensional space and in the presence of strong nonlinear non-Gaussian features. Typically, people try to incorporate a lot of those ad hoc tunings, say noise inflation or localization, and many others. But those things are very empirical. You will never know when to work or when to don't. And so for coupled system with continuous in-time observations, usually we write the system into this form. And if we have the observations of X, and if we want to recover the unobserved state of the Y, so what we do if we try to plug this into the previous Bayesian framework, then this will just be a forecast of Y. This will be a likelihood of this Y given X. So the posterior here will be the conditional distribution of the unknown state Y given the time series of our observations, right? And actually, this distribution has appeared in the previous pages. That is exactly the conditional distribution we looked at in the conditional Gaussian system. So that means if our system can be approximated by a conditional Gaussian nonlinear system, then the target of this data assimilation, which is this distribution, can be solved using closed analytical formula. So that is a motivation which try to let us think about how to build an approximate model using this conditional Gaussian framework, because this analytical formula will allow us to solve this distribution in a high-dimensional space, and we can avoid all those numerical, or at least most of those numerical or sampling issues due to the strong nonlinear and non-Gaussian features. So let me show a very simple example here. Then I will show some more practical example. Let's consider this very simple, only three-dimensional lowered model motivated from the Burgers-Swasinski equation. And here, let's say X, which is the largest scale variable, is our observation. We try to use this model together with a given time series of this X to recover the hidden state of Y and Z, which are unobserved. So this model itself is not a conditional Gaussian model because we have this Y times Z term, right? So for conditional Gaussian, we need to make sure Y and Z they are conditionally linear, but this is definitely not a linear system, not a linear term. That's why we have to build an approximate model for the conditional Gaussian system. And here we consider two different dynamic origins, and their difference is just this noise in the observational process. And usually you will think if we have a small noise, then we'll get good result. But for data assimilation, it's not. Usually if the noise is very small, then you will have a lot of numerical issues. We'll compare three different methods for data assimilation. The first method is we will use this perfect model as our forecast model. So there's no model error, but we will use an ensemble-based method, which is the classical method. And the second method is we try to start from this model, but we approximate this term using the method we proposed previously to build a conditional Gaussian nonlinear system. And then we can use our closed data assimilation, closed form of our data assimilation scheme. And the third method is the worst method. We just ignore this term, right? And you can expect it will not work very well. So first look at regime 1, which is a regime we have sufficient large noise. This is observed time series of X, and our goal is to recover Y and Z. And what I show here is a posterior mean time series. And in principle, we should also have some uncertainties, but I do not show here. This blue curve is truth. The green curve is a method we use a conditional Gaussian approximate model together with its closed analytical formula for data assimilation. This brown curve is when we use a perfect model, but we use an ensemble-based method. So for this regime, basically, it's hard to tell which of these two methods are better. So in terms of the error, the CG method, conditional Gaussian method, is slightly small, but I don't want to say it's perfectly good. Of course, the Bayer truncation method, it is horrible. You can see it misses the truth, right? And this term actually, the amplitude is pretty big, so you cannot just ignore it. You have to use that closure to build an approximate model. But now in regime 2, in which we have a much smaller observational noise, then you can see a difference between the ensemble-based method, even if it is applied to a perfect model, and our conditional Gaussian approximate model. So again, we observe X, we try to recover Y and Z. So blue is a truth. The green curve, which is our conditional Gaussian result, it's pretty close to the truth. But this brown one, it is an ensemble-based method. We use a sufficiently large number of ensembles. We use maybe 2,000 for this three-dimensional system, which is sufficient. But because of that small observational noise, there will always be a few ensembles which will give you horrible results. So overall, this even you use a perfect model, this ensemble method will give you a pretty bad result. And this is, of course, just a simple example which can tell us if we can find a suitable conditional Gaussian approximation, then the closed analytical formula will be very useful in helping us reduce numerical error and the sampling error. And then we can try to apply this to some more complicated system. We use that this framework to this quasi-geostrophic equation or QG equation, which is one of those prototype equations in geophysics. It's a two-dimensional. It's a PDE with x and y coordinates, and this omega is vorticity. This phi c is a string function. They are related by this equation. This j is a advection term. It's a quadratic term. Also, you will have some diffusion and some forcing. So there are two very important non-dimensional numbers. RE is this Reynolds number, and RO is the Rossby number. So we choose a regime where this Reynolds number is about this 450, which is moderate. So you will see some chaotic turbulent behavior, as you can see in this time series. And this RO is a Rossby number. If it's pretty small here, that means your system will have fast oscillations or fast rotations. So that's why you can see these rotations, oscillations in the time series. And if you look at the probability density function, you can see this non-Gaussian behavior with this fat tail here corresponding to these extreme events. And also in other distributions, you have all these extreme events. And these A1 to A6 are the first 6 leading POD mode associated with this system. So the task we are doing here is we try to build a 20-dimension model using the conditional Gaussian framework. The first 10 dimension will be the larger scale modes, which we can observe, but the next 10 dimension, we do not have observations. We want to use this conditional Gaussian nonlinear system to do a data assimilation to recover those hidden variables. And note that the original system is much bigger than this 20 dimension. So we also want to use this cheaper model to reduce the computation cost. Of course, you can see we can start with this model to do data assimilation, but it's so expensive. I don't know how long it will take for us to finish the numerical simulations.
Excuse me, can I ask a question here?
Sure, please.
20 dimensions, do you mean 20 POD dimensions?
20 POD dimension, yes, exactly.
And that's enough to capture basically the dynamics here in this example?
Yeah, in this regime, we can capture like 95% of the energy.
Okay, thank you.
Yeah, that's a good point. Okay, so so I don't show a time series, but I show the spatial temporal recovered field. This first column is a truth. So we use a high resolution QG model to generate true signal, and we project that to the leading modes. Top is a vorticity field, omega, bottom is the string function. And the second column here is data assimilation result after we do the reconstruction using the conditional Gaussian reduced order model, and we use a closed analytical formula. And you can see it is pretty similar to the truth. It's not perfect because we have some approximate error, but it's pretty similar, and you have a good approximation for large scale patterns. And this is a method. This third column is a method we call that Galerkin reduced order model. So basically, we still do the projection, but we completely ignore the closure term. We do a bare truncation for those those terms we should approximate by closure. And this Galerkin reduced model does not have conditional Gaussian structures, so we have to use ensemble method, and you can see it's pretty bad. And as a validation, we also use the ensemble method to the conditional Gaussian framework. So basically, it's called the second column and fourth column. They have the same conditional Gaussian model, but the second column will use a closed form to do data assimilation. But here we use ensemble method, and we also use 2,000 ensembles. So it's a pretty big number of ensembles. This is not too bad, but you can still see some gap between these two columns, especially the error here is by eye at least much larger than this one, right? And of course, this is much slower because we use Monte Carlo methods. And this figure illustrates that CG conditional Gaussian model is a useful model, and also the closed analytical formula will be a very fast scheme to deal with the data assimilation calculations. And this is another time instant. We have a similar behavior. Okay. Then I want to mention another thing, which is called the Lagrange data assimilation. And this is a very widely used data assimilation technique in ocean science. So this is actually a real story for the earliest possible version of Lagrange data assimilation. That is, there was a ship containing all these yellow ducks, which was released had an accident. Then these yellow ducks were released in the middle of the Pacific Ocean. So after a few years, people found these yellow ducks were everywhere. Of course, because they are transported by the ocean current. That's why you can find them everywhere. So then people were motivated by this accident. And nowadays, they put a lot of these devices into the ocean. And these devices will just go everywhere according to the ocean current. And they will send the signals back to the satellite. So you can basically trace the trajectories of all these devices. And the Lagrange data assimilation basically means we try to use observed tracer trajectories to improve the data assimilation of the ocean current. If you do not have these tracer trajectories, what you can do is you use your ocean model to do a forecast. But as I said, for those models, for turbulence, you always end up with a big uncertainty. So if you want to look at distribution, which will be this blue curve, it will have a pretty big uncertainty. But if you can suitably combine this model with observations, you will be able to reduce uncertainty and will have a better data assimilation, right? So Lagrange data assimilation, in this method, the observation will be the trajectories of your Lagrange tracers. And the governing equation is very simple. It's just dx over dt equals v. It's Newton's law. X is the displacement. V is your velocity field, right? And if you think about that in a Fourier space, then you can do an expansion. But once you do an expansion, you will find this is a horrible equation because x is our state variable for the displacement. Once you do the Fourier, then this x will appear in the exponential term. So this equation is a highly nonlinear equation. Usually you can do ensemble method. People will do those tuning, so they won't think this is a big deal in some cases. But this intrinsic nonlinearity will make it very difficult in general to do data assimilation. So what we can do is we still use this equation as our observational equation, but we try to build some approximate model for the velocity field such that the coupled equation x and v, they will be a constant Gaussian equation. And what we need to do is we basically try to use a stochastic linear equation to describe this velocity field of the ocean. So you can see this is nonlinear, but it appears only for the observational variable. So conditional on the observation, this velocity field itself is a conditional linear system, right? And of course, there's a very important issue here. So you want to ask how big is your model error? Because the true velocity field is often very complicated and it should be nonlinear. So of course, there's no rigorous mathematical theorem, but roughly speaking, you will try to use your stochastic noise to characterize the uncertainties come from the nonlinearity. And for data assimilation, because you have your help from observations, So usually using a linear stochastic model is not a bad idea. And importantly, if you have a linear stochastic model together with this highly nonlinear observation process, this will be a conditional Gaussian system. I just want to show a quick result applying that to the sea ice. For Arctic sea ice, we actually do not have a lot of observations using other ways. So we have to rely on the satellite observations for the sea ice trajectories. And unfortunately, sometimes you have a big piece of the cloud. So you will have a lot of missing observations. So practically, it's even more challenging. And what we do here as a test is we treat the ocean as being driven by a two-layer QG, which is very idealized because ocean is more complicated than QG. But still, a two-layer QG is complicated enough for us to test the scale of the conditional Gaussian framework. So overall, we should have like 33,000 of modes here. Then we do not use this QG as our forecast model to do data assimilation because that's way too expensive. What we do is we build the reduced linear stochastic models, and we keep only like 200 modes, which will account for 99% of energy. And these are simple linear equations, and you can run them independently. So you just need a couple of minutes to finish the simulations. Of course, we cannot do a Turing experiment for the QG, but we can do a Turing experiment for the linear system. So there are two curves here. One is the data assimilation scale, where the truth is coming from the QG, but we use the linear model as our forecast model. And another curve is both the truth and the forecast model will be the linear model. But basically, they have similar behavior. And you can see the recovered scale. This is truth. This is recovered field using our linear model, using only 30 flows. Here's 15 flows. 30, of course, will give you a better result. 15 will be slightly worse. But overall, this linear model is pretty successful in helping us to do data assimilation. Okay, so the last topic I want to mention here is about this parameter estimation. And I also want to show how conditional Gaussian framework can be used as a preconditioner instead of just a surrogate model here. So parameter estimation is very important because without the parameters, you don't know how to understand the system and how to forecast the system. And of course, there are many different ways to do parameter estimation. You can use very simple regression if that works. You can do Markov chain Monte Carlo, and you can use your empirical knowledge to estimate parameters. But here, assume that we only have partial observations, meaning that if we have this coupled system, only the observation of X is available. So the method I will discuss here is called the expectation maximization algorithm. So let me try to go into a little bit about the mathematical details. So first, we start with this conditional Gaussian system, and we'll build a method for this system. Then later, we'll see how this can be connected with a general nonlinear non-Gaussian system. And for simplicity, instead of discussing this continuous model, we say we apply an Euler-Maruyama scheme with a very small time step, which just for the simplicity for discussion. And we also assume these are constant matrices and they are diagonal matrices for simplicity. And we use X and Y to denote the state variable, but X hat and Y hat to denote the discretized time series. So parameter estimation with partial observations is very different from the parameter estimation with full observations. So now assume a trajectory of X hat is given. Then with no mathematical structure of this model, our goal is to maximize one of the objective functions. And here we choose the log likelihood to be our objective function. So we want to calculate the likelihood, which is how possible this trajectory is given the parameters, right? You want to maximize it, so the associated parameters will be the optimal parameters. This distribution, you can slightly rewrite it as a joint distribution of X and Y given theta. Then you take the integration of this Y, right? Then you'll get this marginal distribution. And the theta is model parameters. Thus, we can do some mathematical derivations. Say this itself is very difficult to calculate in a direct way, But if we assume we have a distribution function, then we can always multiply this distribution in terms of y, then divided it. Then you apply Jason's inequality, you can put this log inside here. And finally, you will get two parts. The first part is a negative value. The negative value of this will be the free energy, and this will be called the entropy, but it doesn't matter about this definition. So what's important here is, instead of optimizing over this original like log likelihood, we can try to do an iterative method for this f. And recall that what we need to do now is we need to estimate the parameters theta, but we do not know the hidden state y, right? So essentially, we'll have to do two things simultaneously: estimating the parameters and recovering the hidden state. So that's why we use this expectation maximization algorithm. So in each iteration, we have two steps. For the E step, what we do is we try to use the estimated parameters from the previous step, then it's fixed. So now what we need to do is we use a system and the current parameters to estimate the hidden state of y. Then in the M step, we already have the information of this hidden state of y. Then we can do a regression to estimate the parameters. Then we go back to E step for the next loop again. So eventually it will converge at least to a local optimal point. So for this E step, it's an expectation. And essentially you want to find the state of this y, right? And what you know here is your x, which is the observation, and also the current parameter. Since you know the model structure, if you know the current parameter, then you essentially know the model. You know the model and you know the time series. You want to find the state of y, right? So this looks very similar to what we had before. And actually, this is a conditional distribution. This is slightly different from the filtering formula. This is called smoothing. The difference is filtering, you only use observational information in the past, but here we use observational information in the entire training data set. But they have a very similar formula as the one we showed at the very beginning. So for the conditional Gaussian nonlinear system, this distribution can be solved using closed analytical formula. So it's very nice. If we are given a parameter, we can estimate a state using very cheap formula. Then for the maximization, that is, we know this hidden state y. We just need to treat that as something we are given, and also we are given the x. We try to estimate this theta, right? So now you don't need to worry about the hidden variable issue. You can just do like a classical regression method. So a little bit mathematical details. If you consider this coupled system, if you assume x and y are both null, I put x and y into this C. So if they are fully observed, then this is essentially a standard regression. So your maximizing of the log likelihood just give you a standard regression method. It's a quadratic optimization problem. You can solve it directly without any difficulty. But if your y is unknown, then you have to apply the expectation maximization algorithm. And your recovered y will not be a just deterministic value. It will be a distribution. So this recovery will contain uncertainties. So although with y being null, you can do regression. This regression is still slightly different from your classical regression, because now the regression will include an expectation here to account this uncertainty. So the classical regression will be without this bracket. And this bracket, you can think that as an integration, kind of like you plug in all possible values of y, but you assign y a distribution. So it's like an averaged regression method. So your formula will be very similar to the classical regression, but everywhere you should have this bracket. And this bracket will include the statistical information about this y. This framework can also be extended to other improved versions. Say if you want to include a physics constraint, which is very important in a lot of situations, you just do an constraint optimization, and still everything can be written down using closed analytical formula. And you can also do a sparse identification with the saw. Usually you want your model to be as simple as possible. You don't want to overfit your model, so you use sparse regression. which will be naturally applied here. And you can also apply block decomposition to make the system, the covariance matrix to be in a simple form, so you can deal with high-dimensional systems. Okay, so now we need to answer the question how to use this constrained Gaussian nonlinear system as a preconditioner for general nonlinear systems, right? Just recall that the advantage for the constrained Gaussian nonlinear system is that the smoother estimator, the E-step, can be solved using closed integral formula. But this is not true for general nonlinear systems. And in fact, for an arbitrary nonlinear system, computing this continuous distribution is the biggest computational barrier in the expectation maximization algorithm, because you have to use ensemble method. And for big systems, you have to use a lot of ensembles, which will make your calculation almost impossible. So what we do here is we will try to propose a conditional Gaussian model. We call the associated distribution PM, and we call the associated parameters theta m. So remember here, because we propose a different model, so the model using this constrained Gaussian framework may contain different parameters as a truth, but that doesn't matter. So all that matters is we want to use this constrained Gaussian nonlinear system to solve this conditional distribution. Then we'll pass such information to our original nonlinear system with arbitrary form. Then we can do this weighted regression method. So this weighted regression method, all these terms will be based on the original system. But when you take the weights here, then these weights, or this distribution, will come from the constrained Gaussian preconditioner. So you don't need to worry about doing iterations based on the original system. You just need to do the iterations based on the conditional Gaussian system to find these weights. Then you do just one-step regression with the weights given by the conditional Gaussian system.
Excuse me, Nan. I
Yes.
want to make sure that we stay on time and have some time for questions at the end.
Yeah, I think it's almost the end here. Yeah,
Okay.
just maybe 2 more minutes.
That would be great.
Yeah. So just a quick test on the two-layer Lorentz model, Lorentz 96 model, which is conceptual model for geophysics. So the original system is not a conditional Gaussian system, but we try to do a stochastic parameterization for the hidden part, and then it will become a constrained Gaussian model. So we apply the previous techniques. You can see the estimated parameters are pretty accurate, especially we use a non-homogeneous setup here, right? And then you can compare the perfect model with the approximate conditional Gaussian model for the spatial temporal patterns, this one. And then we pass the conditional distribution to the original system to do the parameter estimation of the original model, where the conditional Gaussian system is a preconditioner. And the second column here is a simulation from the original model based on the estimated parameters. So you can see they are all pretty similar to each other. And the time series is also pretty similar. So time series, we don't look at a single path because we use different stochastic noise. But overall, you can see blue is a truth. The green one is identified model, where the constrained Gaussian model is used as a preconditioner. And this orange one is the approximate model using the constrained Gaussian formula. You can see it can capture all these non-Gaussian, Gaussian and non-Gaussian distributions and all these autocorrelation functions. Okay, to summarize, so we propose this conditional Gaussian framework, and we want to apply that to different topics, which show that it can be used as a preconditioner or a surrogate model. And there are also a lot of other applications which I don't have time to show. In fact, one thing I want to mention is it can be applied to solve the high-dimensional Fokker-Planck equation. So this model can be used to do ensemble forecasts and try to predict a linear response in high-dimensional systems. And also it can be applied directly to many other geophysical phenomena. I guess that's the end, and these are the references. And thank you very much for listening to this talk. And I will stop here. Thank you.
All right, thank you very much. Are there any questions? You have 5 minutes for questions. Maybe I can start. So for the conditional Gaussian with ensemble Kalman filters that you had an example of at least.
Yeah, I go back to that page.
You draw your ensemble from your closed form conditional Gaussian. Is that the idea?
The idea is we do not use ensembles, but instead we use, let me go back here. Yep, we use this formula directly to compute the mean and the covariance. So if you do not have this closed formula, then when you try to approximate a distribution, you have to rely on your ensembles, right? And in high dimensional system, you have this famous cursor dimensionality issue. So you cannot afford a lot of ensembles. So here we can avoid all those problems by just plugging the model formula to the right-hand side. Then we solve this conditional distribution based on this formula. So there will be no ensemble being used here. And that's why in this simple example, you can see in this case, the observation noise is very small. So in the situation that your ensembles will collapse, like some of the ensembles will go just towards to the same value, and maybe some of the ensembles will diverge. And that's why, when you use this ensemble-based method, this brown curve, you have some weird behavior.
But I was asking particularly about an example where I think it was a couple of
Yeah. I have another. You mean this one, right?
Yeah. Here you use the fourth column. You use conditional Gaussian ensemble Kalman filter.
Right. Here, yes, we use the ensemble method. Basically, we want to check, what's the difference between, using the closed form and the ensemble method. And yes, here we use ensemble method, but we use a large number of ensemble method. And in this case, like you can see the time series or the distribution. This is non-Gaussian, but it's not crazily non-Gaussian. The Reynolds number is like 450. Right? If we further increase this Reynolds number to make it even more non-Gaussian, then the ensemble method will suffer from even bigger issues.
Gotcha. Okay.
Yeah. So the overall take-home message is, if we can avoid ensemble methods, then we should avoid it. It's not just for the accuracy, also for the computational cost, because you have to run a lot of ensembles using Monte Carlo simulations. It will take a lot of time.
Yeah. Other questions?
And that equation that you have shown answering the previous question, I think it was one quantity that was never defined previously. Can you scroll back?
Okay, which one?
The one for the moments, the system of equation, which is
you mean here?
Yeah. What is this capital R with double bar in the first equation?
Sorry, it's a typo. It's just R.
Okay.
Yeah, sorry for this. Yeah, I use different notations in my paper and try to adjust them. Yeah, this is a very, very good question. I should correct it. It's just R. So your main equation will be driven by your covariance. So they are not decoupled.
And perhaps a more general question. So when when you started talking, when you consider a system with turbulence, and then you split the quantities according to scales, and then you started building closures. So does it have anything in common with, there are all sorts of closures out there. If you want, in engineering with all turbulence models that are used for simulations, and then if you go back to Bogolyubov system and statistical physics, can you build any parallels here?
Yeah, that's a good point. So my understanding is usually in most of those closure methods, you just try to use a deterministic way to model them, right? And also when you build a closure, you care mostly about a forecast uncertainty, forecast accuracy. But here, the purpose of building this very special type of the closure, which is here, is we not only want the forecast scale to be good, but also we want this model to be skillful in recovering some hidden states, meaning that we want the data assimilation or state estimation to be taken into account as well here. So the starting point is slightly different from the classical closure methods. And that's why we prescribe this conditional linear closure terms here. But of course, we should try to compare such kind of method with the state of art method and to see what's the advantage or what's the error due to this special form here. That's something we should try next.
Thank you.
Yeah, thanks for this great question.
All right, maybe we should wrap it up in the interest of time. Thanks so much, Nan, again, for the very beautiful talk.
Thank you very much.